So once we have these weight vectors initialized, then we can have a training vector, or we can consider different training patterns in order to calculate the weights. So consider a simple example in which there are only 4 input training patterns, right? So for this example, we have these 4 training patterns. So we are representing them with x1, x2, x3 and x4 here, and we can have the learning rate at time t plus 1 can be given as learning rate alpha at time stamp t plus 1 is equals to the learning rate which was at time t divided by 2. So we are basically reducing our learning rate with each time step here, and we can suppose that our initial learning rate with at timestamp t is equals to 0 is 0.6, right? So we have our initial learning rate here which is being set as 0.6, and this is at time interval t is equals to 0. And for the next time step, which is at t plus 1, we are basically reducing it 50% here in this example. And we can also consider that for this specific example, we have our topological radius which is being represented with r here is equals to 0. Now, following the algorithm which we have seen in the previous slide, we basically needs to calculate the Euclidean distances, and then based on those distances we need to update our weight matrix. Now we will take each vector or each training pattern one by one, and we will compute their corresponding distances. So for weight vector 1 1 0 0, which is this number 1 pattern, which is 1 1 0 0, we are using Euclidean distance and squared. As you know that we have squares in the Euclidean distance, so we will be using the same, and we will calculate d1. So d1 will be computed against the first weight vector, right? So we are using this weight vector which is 0 0.2, 0 0.6, 0 0.5, 0 0.9 for our initial training pattern which is 1 1 0 0. So this will become 1 minus 0 0.2, 1 minus 0 0.6, 0 minus 0 0.5 and 0 minus 0 0.9. So when you will be computing this equation, it will turn out to be 1.86, right, for d1. So this is the distance of our first training pattern and our first weight vector. Now we also need to compute the distance of our first training pattern with the second weight vector, and when you will compute this by the same formula, it will turn out to be 0.98. And now you can figure out that for j is equals to 2, we have the minimum distance, right, because this value is less than this value. Hence we have j is equals to 2. So we have computed our index basically, which we discussed in the algorithm. So for j is equals to 2, we have already r is equals to 0. So we need not update the weights of any neighboring neurons, and this is the equation of our weight in order to update the new weight matrix. And if we use this equation to calculate the new weight matrix, since we have our index j is equals to 2, so we can have our previous weight, and by putting all the values in our updating weight equation, we can calculate basically the new weight vector, right? So the first value will be here 0.92, 0.6 is the learning rate, and 0.8 is basically the old weight vector, and through this equation we can update all the weight vectors. So now we need to repeat these steps for all the training vectors, right? So we have seen that for our first training pattern, which was 1100, we computed this stuff. Then for our second weight vector, which is 0001, we will calculate distances. So those distances will come out to be 0.66 and 2.2, and we can see that the minimum distance or the index is 1, so j will be 1, and we can update the weights accordingly. Similarly, for the third pattern 1000, the j will come out to be 2, and for the fourth weight vector, which was 0011, we can see that our weight vector will turn out to be the j value will turn out to be 1, and we can update the weights accordingly by using the same weight updation equation. Now once we have computed all these things for all the training patterns, so the next thing is that we need to reduce our learning rate, right? So you remember that we have defined an equation through which we will be reducing our learning rate for this specific example, and for this specific example we are basically reducing our learning rate by 50%. And so if the initial value of the learning rate or alpha was 0.6, then after reducing the learning rate it will turn out to be 0.3, and then after reducing the learning rate we will basically repeat all the steps again, because we are repeating these steps in a loop until we met to a stopping criteria. And for this specific example, if you will repeat for 100 cycles or for 100 epochs, then you can see that the input vector will give you the final weight matrix, right? So the final weight matrix will be similar to this one, and you can see this matrix can converge to this weight matrix, and we can use this weight matrix in order to divide, or in order to group our input data set into two clusters, right? So because we have two output neurons and we have two weight vectors, so we will be forming two different clusters, and our input patterns after completing these 100 iterations, it will be successfully clustering into two clusters. So you can also test your trained network. So in order to test our trained network, what we can do is we can provide an input pattern, a test input pattern, which is 1100 in this case, and we can see that whether our matrix is converging or not, right? So we can use the same formulations which we have already used. We can use this weight matrix which we have achieved after 100 iterations, and we can compute the Euclidean distance of the input pattern with both of the weight vectors of both the resultant weight vectors. And when you will compute all these distances, you will see that the neuron 2 is the winning neuron here and is the localized active region of the SOM. Notice that we may label this input pattern to belong to cluster 2. So once we know that this pattern 1100 belongs to cluster 2, then we can assign its output class or output cluster here, right? So we can say that this pattern belongs to cluster 2, this pattern belongs to cluster 1, this pattern belongs to again cluster 2, and this pattern again belongs to cluster 1. So we have two patterns belonging to cluster 1, and we have two patterns belonging to cluster 2. And for all the other patterns, we can find the clusters which are listed below, right? So let's have a look at a practical application of a SOM algorithm.